Okay, in this podcast, I'm going to go over worksheet 4, specifically problems 1 through 10. And then I'll do a subsequent podcast where I do the rest of the problems in that worksheet. So question 1 says, what is the molarity of lithium ions in a solution prepared by dissolving 2.2 grams of lithium sulfate? We're given the molar mass in enough water to make 50 milliliters. Okay, so we're looking for the molarity of the lithium ion. And one of the things we've got to remember is if I'm taking lithium sulfate and dissolving it in water, I end up with 2 lithium plus 1s. For every 1 mole of lithium sulfate, I get 2 lithium plus 1. So I can solve this for lithium sulfate, and then I got to double whatever amount I get. Okay, so my answers are reasonably close to each other, so it's going to take a little bit of thought here. I'm going to take my 2.2 grams of lithium sulfate, and the molar mass that I'm given is 110 grams per 1 mole of lithium sulfate. Okay? So if I want to find molarity, I got to get moles and divide it by liters. So this is going to give me the moles. And if I look at this, if I had, say, 1.1 gram of lithium sulfate, I think you can see that that is going to be not a tenth of a mole, but 100th of a mole, right? So it's going to be 0.01 moles, right? But I have 2.2, so it's going to be 0.02 moles, right? So 2.2 over this is going to be 0.02 moles. Okay. So I'm going to take that 0.02 moles. This is lithium sulfate now, right? And I'm going to put it over liters. So if I had 500 milliliters, it would be 0.5 liters. But I've got 50 milliliters, so it's point. All right, 0.05 liters. Okay. So if I take this now, I can cancel out the zeros, right? So it leaves me with 0.2 over 0.5. Now, a lot of you can look at that and say it's 0.4, but you could also think about this as 0.2. And if I take that 0.5, that's really a half, right? And if I'm dividing something by a fraction, it's the same thing as 0.2, and I invert the 1 and the 2. Times 2 over 1, which gives me 0.4. So I have 0.4 molar of lithium sulfate, but I have twice as much molar of the lithium ion. So this answer is 0.8. That's a pretty tough problem. All right, let's take a look. Okay, which equation best describes the net changes, key word here, net changes, based upon the observation that solid silver nitrate and solid potassium chloride are soluble in water. So they're going to make an aqueous solution. These solutions react to form insoluble silver chloride and soluble potassium nitrate when mixed. Okay. Lots of key words in there. So first thing, the one thing that I know I got to have is insoluble silver chloride, but it turns out all the possibilities have insoluble silver chloride. They're talking about the solutions reacting, so that's a key there. They're not putting solid silver nitrate and solid silver potassium chloride together. They're putting the solutions together. So I can eliminate choice A and B because these have the solids going in, which leaves me with choice C and D. Now it talks about the net changes and which equation best describes. And the folks in the AP always believe that the net ionic equation is the best way to represent what's actually happening because it only shows those participants that are actually reacting, and it does not include spectators. So the spectators have been removed. So the answer is going to be spectators do not get shown. So the answer is going to be D. Okay. Which pair of samples contains the same number of oxygen atoms in each compound? So if I have 0.1 mole of Fe2O, I'm going to have 3 times as many moles of the oxygen because of this 3 here. So I'm going to 0.3 moles here. 0.5 moles of BaO will also give me 0.5 moles of oxygen. So I have 0.5 there. I'm talking about oxygen atoms, okay? If I take 0.2 moles of Br2O, that's going to give me 0.2 moles of O. 0.2 moles of HBRO also gives me 0.2. So my answer is B. Now, if you're confident, you can just stop right there. Now, if you weren't so sure, you could look at the next ones and say 0.1 moles of NaO gives me 0.1 moles of O. 0.1 moles of sodium sulfate, I got to quadruple that because of the 4 here. So those are not going to be equal. 0.1 versus 0.4. And this one I had you change because it actually could have been the correct choice if we didn't change that to a 3. So 0.2 of barium hydroxide is 0.2 times 2 because there's 2 O's in here, 0.4. And 0.1 times 3 is 0.3. So this is not the same. So the answer is B. Okay, let's take a look at number 5. Number 5 is actually pretty complicated. It says a precipitate is formed when 1 liter of 0.2 molar potassium phosphate is mixed with 0.5 liters of 1.6 molar zinc nitrate. After the reaction occurs, which list ranks the ions remaining in solution in order of decreasing concentration? Okay, so I think this deserves a ICF table or an ICE table, whatever you want to call it. And so I'm just going to rewrite the equation. It gives me, the key thing here is I want to make sure that I identify that this is a solid. Okay, so if I just look at what I'm starting with, I'm starting with 1 liter of 0.2 molar. So remember, moles, because molarity is moles over liters, moles is equal to molarity times liters. So 1 times 0.2 for potassium phosphate gives me I'm starting with 0.2 moles. Okay, and let me see, for zinc nitrate, which we said it should be manganese nitrate, right? We have half a liter of 1.6 molar, so 0.5 times 1.6 is going to be 0.8 moles. And of course I start with none of this and none of this. So if I'm just thinking about what's limiting, if I have 0.2 moles of this, then I'm going to need 0.3 moles of this, but I got way more than that, so this is going to be excess. So I'm going to use all of this, okay? So if I use 0.2 of this, I'm going to need 0.3 of this, so none of this will be left, and I'll have 0.5 of this left. Okay. Now, if I'm making 0.2 of this or 0.3 of this, I'm going to make 0.1 of this, and I'm going to make 0.6 of this. Okay. Now, the important thing to recognize, so I'm going to end up with 0.1 of this and 0.6 of this. But within this, you know, I have 2 different ions with different concentrations of each ion. But you might pick this up or not. There's lots of different ways to approach this. But here, I have some solid at the end, but there are no ions floating around. So I essentially have no ions coming from here, right? And because this is limiting, I also have no phosphate at the end. Okay? I have no phosphate at the end. So I'm going to have no phosphate here, okay? And all of this potassium is going to get converted to potassium nitrate. So if you look at your choices, the one that has the lowest concentration of the phosphate is A, and that would give you the answer for A. Now, if you didn't quite notice that, and you had to think about how much of each ion you have, here's how I would do that. So I would say, so if I have 0.5 molar of manganese nitrate, I have 0.5 moles of manganese, but I have twice as much because of this 2. I have 1.0 of the manganate ion, right? Sorry, of the nitrate ion, because I've got this 2 nitrates for every 1 manganese nitrate. And I'm going to have 0.6 moles of both potassium and the nitrate here. So as you can see, when I look at what I have left, I have no excess from potassium here, but I do have some produced over here. So the thing I have the most of is the nitrate, which would narrow it down to A and D. And then after that, I'm going to have the most is going to be potassium. Okay, so A and D both have potassium. There is a choice. Followed by the manganese. So the answer is going to be A. And I have no phosphate left. Tough problem. Actually, I'm going to stop right there.